Hi there, my name is Finn Yek, and this is my video lab report for Lab 3 for Physics 2212. So here's just a brief rundown of what's going to go on in this video. I'm going to introduce our experiment, which is going to include relating all of the relevant equations and principles and detailing the experiment setup. And I'm going to show some experimental data that was obtained from the experiment, which will include calculations and some results. And I'll talk about these observations. Then there will be a computational model, which is the GlowScript code, and it'll show the output. And then we're going to discuss some results and talk about some other potential impacts of this experiment. So first off, some key ideas is the bar magnets, which is just a magnetic dipole whose equation for the magnetic field generated at a distance z here is given by mu naught, which is the magnetic constant over 4 pi times 2 mu, which would be the magnetic dipole moment over z cubed. Also important is the superposition principle, which allows the magnetic field, the net magnetic field at a point is given by the sum of the magnetic field due to all components that contribute magnetic fields at that point. So you can just add them up. And then the experiment itself, we're just going to be using a phone magnetometer, an app to measure the magnetic field produced by a bar magnet at several known locations. And then I'll be comparing the magnetic field at different radii and orientations. Here's some lab data. You can see here the distance is obtained, or for several distances, the magnetic field data is obtained and the average is taken from that. And then we graph it logarithmically with the logarithm of the magnetic field average versus the logarithm of the radius. We get these data points, and a line of best fit of this is given at y equals negative 3.2958x minus 1.6797. And here that constant negative 3.2958x shows kind of the dissipation of the magnetic force as the radius gets larger. So you can see that the farther away the magnetometer is from the bar magnet, the lower the reading it's going to give. Yes. So here's just some things. So when the magnetometer is far away from the magnet, it measures the near zero magnetic field in the X direction. This is correct because, or this was seen in the experiment because since the magnetic force is less strong at a larger distance, if you move it far enough away, it will approach zero. And the magnetometer moves closer to the magnet. The measured X component of the magnetic field decreases. Is actually incorrect. As the radius is smaller and making the X component, as the radius is smaller, all components of the magnetic field should increase. The position of the magnetometer has no effect on the measured X component of the magnetic field. This is incorrect, as stated above. It will make all components that have any component that have any magnitude, it will make them larger as you move it closer. As the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. Correct. Here's some code. So this is just inputting some of our data, some of our average data into the equation to generate the magnetic field at a point or distance r from the bar magnet, and it models out the bar magnet. Down here, it's printing out these values into vectors. Some extra questions. What if you hadn't oriented your experiment to compensate for magnetic north? You had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field. How would your results have changed? So they may not have changed too much, but the initial, I suppose, value for the magnetic field would have been different, and there would have been components in the X direction as well as the Z, or as well as the Y direction. So the impact of the bar magnet would have been less clear because there would have been other components. So you would have had to do some trigonometry to get the exact effect of it. And what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? So there would be two dipoles here. And depending on the orientation of it, you would have to use the law of superposition to determine the net magnetic force at a distance r from this configuration. And if you, depending on how you oriented them, you could actually cancel it out and have no effect on the magnetic field at that distance r. You could orient it so that it would be twice the distance r. It depends on how you oriented them. Thank you very much. This concludes my lab report.